So I have two steel balls, and I'm going to launch them simultaneously. Now this one is threaded on the end of this rod right here. When I flip this switch, there's a spring load, and so this thing is going to shoot, the rod is going to shoot off to my left. It's assumed that the friction in the ball right here between the ball and this rod is small enough so that basically that's going to just shoot right out, and this is going to fall close enough to straight down. It will not be exact because, well, frictionless does not really exist here, but it should be close enough. It's like pulling the tablecloth out from underneath dishes on a table. The dishes will move some, but if you do it fast enough, it won't move much. On the other side, I'm going to place this ball, and this ball is going to be shot off to the right. So one's going to fall straight down, the other one's going to be shot that way. So technically, they're going to be released close enough to the same time so that this one will start to fall and this one will be projected close enough to the same time. So the question is, which will hit the ground first? So I got the one that's going straight down and the one that is being launched. So I guess your options are, there's the one falling straight down, the one being launched, tie, and what the heck, we'll do the burst into flames as an option. So have an opinion, and then we will vote. Who says the one that drops straight down? Who says the one that's launched? So I got 3, and Zoe, you're not willing to commit? Look like you're starting to go for it. I'm not trying to force you. A tie? Neither? Was there a vote for neither over there?
No.
We should be able to hear it when it hit like that. For people, I guess, in this viewpoint right here, is that level?
Yeah.
All right, here we go. Okay, part of that hit the platform there. I think you got the gist of the answer as it is, but let's do it again where it's not going to hit the platform. And I'm going to tilt it that way so that I don't think it's going to get that far, but I don't want you to think I'm aiming at you. Oh, no, that's one still falling down. All right, level-ish, good enough. So which one hit first?
I think they both did at the same time.
All right. Theoretically, if everything were done perfectly, yes, the 8 would have done it. But the one that's being launched, isn't it traveling faster?
Yes.
Yes.
Okay. So how do they hit at the same time if the projected one is traveling faster?
Because it's not going straight down, it's going kind of like around. I guess
You want to expand on that?
it's being shot out. I mean, I don't know if it's.
Okay.
I don't know how to just like put in what you're expecting me to say. I wish I was there.
Is it going around at curve so its velocity slows down?
No, it doesn't slow down, but it is traveling faster indeed. But it also has farther to travel. And so the time ends up being the same. All right. That would have been more succinct than you were basically there. once I've flipped it, what are the forces acting on the two balls?
Wait.
Yeah, they each have their own weight. Well, weight one and weight two. And weight is acting straight down. They're both experiencing the same acceleration, straight down. Horizontal velocity and is not being affected by acceleration that is straight down. Only vertical velocity is affected by vertical acceleration. So they fall at the same rate. So in this picture in the book done with a strobe effect, where you have the ball being shot and dropping at the same time, and you can see at the same time they are still at the same height. Now this works if you were launching it horizontally. If you shoot it vertically, yes, there's a difference because now you've got an initial vertical velocity. So we can figure out how fast this thing was shot easily enough. Well, let's first figure out how much time it takes for it to fall. Now, if we use stopwatches to figure out how much time it takes for it to fall, we are going to probably fall a little short. I have found from experience that anything under a half a second, human error, human reflexes really become much more significant. So we're going to actually figure out the time by calculating it. Flashing back to chapter 3, we have an object that, well, the time it takes for an object to fall this distance, probably the bottom of the ball, so wherever I put it. So from the table to the bottom of the ball, it's 55.2 centimeters. So this distance, 55.2 centimeters, but meters probably going to be preferred here. So 0.552 meters. Acceleration due to gravity. Since we're doing an actual experiment here, let's use the actual value, 9.798 meters per second squared. And we're going to use the formula from chapter 3. I think this was the last or next to last formula that Hewitt wrote down. He wrote it as d equals 1/2 gt squared. I would write it as delta x is equal to 1/2 at squared. Either way. This is the formula you use if you have an object basically in free fall starting from rest. And it was. That there was no vertical, so it was basically starting at rest and falling. So we have 0.552 equals 1/2 times 9.798 t squared. So mathematically, let's do this first. What is 1/2 of that? 4.8 something. If someone would be kind enough to let it.
4.899.
What is it?
4.899.
899. T squared. We're trying to get the t, so we need to start hacking away at the things around it. So let's first get rid of this, 4.899. 4.899. So on the right-hand side, I'm left with just t squared. And over here, I get whatever that is. What, 1 something? And now we just have this t squared, so we have to get rid of the squared by undoing it, so we do square root of both sides. And whatever the square root of 0.1126 is?
0.3355.
Units?
Meters per second square, or just seconds?
What was the last thing you said?
Would it just be seconds?
It would just be seconds.
Okay.
So this thing's gonna fall in 3.3355 seconds. So when this thing gets shot out and lands, again, the acceleration is downwards. There's no horizontal acceleration at all, which says that the horizontal velocity does not change. So we can use another formula from Hewitt. Basically, distance equals rate times time. I'll write it in the physics way. If acceleration is 0. If there's no change in velocity, then just take how fast I'm going times how much time it took, and it gets me how far it goes. Except in this particular experiment, while we know time, we just calculated that. We're going to measure that, and we're going to calculate the speed. So then the question becomes, where does it actually land? Let's do this incredibly scientifically by eyeballing it. Actually, that's the point in which the force is no longer on it. So that's what I want it lined up with. All right, Gabby, I think you have the best point of view there. Does it look like the ball is lined up with the edge of this?
Yes.
Okay. And do you recall how far out it shot? Do I need another meter stick? Pardon?
It looked like it, like, I don't know.
You might need another meter
Yeah.
stick. I feel like it was right around there.
We can just move it down. I doubt it's gonna shoot like right underneath it.
Well, I have it now. All right. Chansey, you're gonna have the best point of view. However, I guess the 6 of you probably have the best point of view. Let's see if we can get consensus about where the thing actually lands. With luck, it'll land on the meter stick. Here we go. That was sort of.
I was completely wrong.
So, do we need to do it again?
Bless you.
Thank you. It was somewhere around here.
Yeah, it was like right
Yep.
before the crack in the table.
All right, let's see if we can nail that down a little bit better.
We definitely did not need a second meter stick.
Yeah, that's the way it seemed right now. Here we go. I think I must have done something wrong the first time.
It was like right here, I remember. It was right where that line is, so it was like right here.
Right there?
Yeah. Well, from
Yeah,
where
that's
I could
what I
see,
saw.
yeah.
All right, are you good with that, Chansey?
Yeah, that's exactly
All
where
right.
it was.
So that was right around here,
A little bit further than that. I
Yeah,
can't
right
read
there.
it, but
Right there.
right there. All right, so that is 77.5 centimeters. So I've got 77.5 centimeters, or 0.7775 meters is equal to whatever that initial velocity was, because it was all horizontal, times 0.3355 seconds.
What is that arrow in for? Can you remind me? Like, is that just the,
This arrow right here.
is that the average or?
Oh, no,
Change?
with an arrow, it's indicating it's a vector. We're talking about velocity.
Oh,
It also works in this particular case with speed, since it's only going in one direction horizontally. Average would just be a straight bar without the head.
okay.
So what do we get?
Okay. I just just got 2.309.
2.309 units?
Meters per second.
All right. So the thing goes blazing out of there at a little more than 2.309 meters a second, which is around 5 miles an hour. I don't know if you've done any lab where you shoot stuff where you find the speed doing this, basically the same technique. Have you done any of those labs?
I mean, we ran.
Yeah, I
but
did like one
that's
where
it.
you walk in front of like a sensor and then walk faster and slow down.
Oh.
That's the same thing, but.
There's another one that I do when I do the labs around this time where you actually shoot these projectiles using a projectile launcher that, one of those things that can launch it across the room, if you got room to do it. Unfortunately, there's people in the way.
The only other one that we've done that like kind of involves this is where we swing you over our heads, but
The centrifugal motion one.
yeah.
Yeah, a little bit different, because unless you let go of it, it has to be using the projectile launcher, so I guess you have not used the projectile launchers?
No.
Okay. I also do the projectile launcher labs because sometimes I'm just in the mood to shoot things. Shoot the steel balls, I'm not shooting people. All right, so let's take this idea. Oh, any questions before we extend this idea? All right, so let's take this idea of launching something. We'll get back to the planet right there. If I shot it faster, what's going to happen? Not a trick question. If I shot it faster, what would happen?
Who goes
It's going
farther?
further.
Yeah, I would hope so. And shot it faster?
Even further.
Yeah, all right. At some point, all this is well and good. What we just did here worked really well for long distances. However, at some point, the curvature of the Earth will start to have an effect. First, let me drop back for just a second. The whole idea of something falling and landing at the same time, Mythbusters did an episode where they shot a bullet and it had a bullet drop at the same time. I really was expecting a much bigger difference when you bring air resistance into account. It did not. It was amazingly close, even with, because bullets typically, at least with a rifle, they take advantage of air resistance. It spins for a reason. But I guess it reduces the air resistance to close to as little as possible. All right, so anyway, back to curvature of the Earth. So if I take the curve of the planet here and I'm shooting off from the top of the hill, at some point, the curvature of the Earth is going to render what we just did of timing how long it takes to fall completely wrong. Now, Newton speculated that if you shoot something fast enough, so if I got a whole whirl here, if I shoot something fast enough, it will just go all the way around. I cannot remember the name of the book. I wish I could. It was either, I think it was The Phantom Tollbooth, where somebody flew by throwing themselves at the ground and missing. That's basically what's going on here. We have an object that's constantly falling, but it just keeps missing the Earth. If it is shot fast enough so it can go all the way around and come back, this is known as a satellite. By this reasoning, the moon is falling, but fortunately it's traveling fast enough that it just keeps missing. Now, once it is launched, similar to escape speed, once it's launched, I don't care about how it got launched, all I care about is once it is launched. Once it is launched, if we look at the forces acting on our satellite, what are all the forces acting on the satellite as it's traveling around?
Force due to gravity.
And then there's a force due to gravity acting back on it. I mean, the moon does cause a little bit of a wobble on the earth, but we most notice it with the pull of the tides. Any other forces?
Actually,
On with,
I don't know, I'm just assuming that the problem would be doing my friction unless we said frictionless.
alright, so we've got our checklist here. And I guess we had buoyant and spring. No springs involved. Weight definitely is involved, or gravitational force. Friction requires rubbing against something else, or if you're talking about air resistance, hitting air molecules.
Air resistance.
Air resistance. We will assume, because this is a nice board problem, we will assume that there is no air resistance. That probably Newton, I suspect Newton had difficulty imagining this actually being done practically because of air resistance, but at this point we know if we go out far enough, air resistance becomes so incredibly insignificant. You have to worry about other things at that point, but. So no friction to speak of. Tension? Not unless there's an invisible string there. You know, someone twirling this thing around like you did in your lab. There's not another. Normal force?
No.
Has to be touching something. Springs? All right, so we just have this one force acting on it. Hey, wait a second, this is circular motion. What's the other word we have for circular motion?
Centripetal.
There we go. It is centripetal motion. So let's go back to Newton's second law. What is Newton's second law?
Object in motion.
Inertia? Object in motion.
That's one. That's the first law.
Oh, is that
Oh.
the one